Chapter 19 of the Rust book does a great job of explaining pattern matching and destructuring. So in this video, I'm only going to discuss a couple of areas that I personally had to spend a bit more time on. This will be different for everyone, and is more a function of the amount of new information involved in learning a new language like Rust, rather than any real shortcomings in the Rust book. The section in Chapter 19 that covers @ bindings has this example. And my first thought was, why can't the first match arm be this? That is, why can't an @ binding use the shorthand syntax of omitting the struct field name when the binding variable has the same name? The shorthand syntax is used in the third match arm. Here's an equivalent scalar version of the previous match expression. And if you compare the match arms, you'll see that it's actually the third arm that's the odd one out because of the use of shorthand syntax. The first two arms explicitly include the struct field name in their patterns, and the third doesn't. This destructuring shorthand mirrors the struct construction shorthand, where the field name is also omitted when initialized with a variable of the same name. When we omit the shorthand syntax, then our enum destructuring and scalar destructuring mirror each other in all match arms. So that leaves the question, why is the shorthand syntax only allowed in the simplest binding case? The short answer is, to get the greatest benefit with the least effort and least amount of additional complexity. The construction shorthand syntax is the most common use case, and destructuring exactly mirrors that. Anything beyond that would involve greater complexity for the compiler while providing diminishing returns for developers. The second area I want to cover is ownership and borrowing in relation to pattern matching and destructuring. Remember that let statement bindings are pattern matched in the same way as match expressions. Here's an example of a let binding a variable j to a copy of the value of a variable I. I is of type I32 and so implements copy. This let binding demonstrates the simplest possible pattern where the variable name j is the whole pattern and so no destructuring occurs. J is bound by copy to the value of I, so j will be of type I32. In this example, j is again the whole pattern, so is bound to the immutable reference to the value of I. And so j will be of type reference to an I32. Here the pattern includes the reference symbol before the variable name j. The value must match the pattern, meaning in this case that the value must be a reference type, which it is. Destructuring against this pattern will strip away the reference, with the result of dereferencing the expression to the value of I, which is then bound by copy to the variable j. J will again be of type I32. In this example, the pattern also expects a reference type, but the value is of type I32 and so does not match. This will generate a compiler error. The ref keyword is not used much for new code on modern versions of the Rust compiler. I'll talk more about this later, but in the context of the let binding of primitive scalar types we've looked at so far, this statement has exactly the same effect as this statement. In describing the first statement using the ref keyword, we would say, bind j by reference to the value of I. But for the second statement we would say, bind j to a reference to the value of I. In the second statement, the reference is already part of the value, but in the first statement, the reference is introduced through the pattern and the binding process. But the end result is exactly the same. So far, we've been destructuring with values that are copy types. But what about non-copy types, like string? In this example, S2 is the whole pattern, so is bound to a copy of the value of S1. But S1 is a string type, which does not implement copy, and so move semantics apply. As a result of the value of S1 being moved rather than copied, S1 is no longer valid. The resultant type of S2 is a string. In this example, S2 is again the whole pattern, so is bound to the immutable reference to S1. So S2 is of type reference to a string. You might think that this next example should work. In the case of the equivalent primitive scalar type involving a reference pattern and a reference value, the pattern caused the reference to be stripped away, binding a copy of the dereferenced value. Here the pattern is valid as it matches the type of the value. But the value causes a compilation error, cannot move out of a shared reference. If the compiler allowed it, this code would actually be safe and produce the expected result of moving the value of S1 and binding it to S2. But this is not allowed because moving a value out of a reference that is bound to a variable would leave that variable with an invalid reference. Now, in this case, our reference is not bound to a variable, but the compiler still enforces the rule for simplicity and consistency. Let's look at more complex examples involving match expressions and structs. Here we're matching this instance of a toInts struct against this pattern. The pattern will destructure the toInts struct, leaving its fields I1 and I2, which are then bound by copy to the variables I1 and I2. I1 and I2 will be of type I32. In this example, you might expect a compiler error, because an attempt is being made to match a value that is a reference type against a pattern that does not include the reference symbol. But this code will actually work, and destructuring will result in the variables I1 and I2 being bound by reference to the corresponding struct fields. I1 and I2 will be of type reference to an I32. The reason this works is because of the introduction to Rust of a feature called match ergonomics. With match ergonomics, if you have an instance of a complex type such as a struct, and patterns that match that type, then you can choose to match against a reference to an instance of that type, and the resulting destructured field values will be bound by reference rather than by copy. To get this behavior prior to the introduction of match ergonomics, you would have had to use a pattern that explicitly matched the reference and then used the ref keyword modifier to force binding by reference rather than by copy. Note that ref has no effect on whether a match is made, but only acts as a binding modifier. This syntax is more verbose than with match ergonomics, but it's also more explicit and immediately obvious. Similar to the scalar let binding example earlier, this code won't compile. The value is an instance of a toInts struct, but the pattern is expecting a reference. Match ergonomics only works and only makes sense when the value is a reference and the pattern is not. This example does work in the same way as the scalar let binding example. The value is a reference to a toInts struct instance. The pattern strips away the reference and struct, resulting in the variables I1 and I2 being bound to copies of the corresponding struct field values. I1 and I2 will be of type I32. This example involves an instance of a struct with fields of type string, which is a non-copy type. The pattern matches the value, but this time the binding involves values of the struct fields that have been moved rather than copied. This results in the struct fields no longer being valid. Variables S1 and S2 will be of type string. Here we are matching a reference value against a reference pattern. The pattern matches the value, but since the binding would result in a move out of a reference, this will result in the same compiler error that we saw with the earlier let binding example. However, match ergonomics still work to allow easy borrowing and subsequent use of the original struct. Thanks for watching, and please like and subscribe so that you don't miss out on the next video, which is on the subject of the deref trait.